Hello there, wind power students, and we're getting very close to the end of our course here in wind energy. We're in the 8th module where we've been talking about modeling, which in some ways is kind of silly. I mean, practically everything that we learned in this course was really a model. We didn't tend to use that verbiage along the way, but whether we were talking about like the log wind profile or how wind profiles change as we went over from one surface to another or whatever, what we were really talking about was a type of model, a way of simulating the behavior of the real atmosphere without actually going into all the physics and so on. Now, in today's lecture, what we're doing is we're talking about a very specific type of model that has very concrete application in the wind power industry, and that's numerical weather prediction. Now, we're generally going to use the acronym here, NWP. Numerical weather prediction, or NWP, is the business of using the full physics of the atmosphere to simulate what the atmosphere is doing. NWP is how we get the day-to-day forecasts that you see on television or hear about on the internet or whatever. I just happen to have an example of a diagram here, and exactly when and what this all is and so on. It's not so important as to understand that this is the graphical output of a numerical weather prediction model, where it is actually simulating what the weather is going to, what the atmosphere is doing. It knows the rules that are the behavior of the atmosphere, and then it is computing, in this case, it happens to be absolute vorticity and heights and wind of the 500 millibar level. That in and of itself is not so important as the idea that, see, the computer is simulating what the atmosphere is going to do in some point in the future. This happens to be a 60-hour forecast of a particular model called NAM. NAM is this strangely named North American model. But anyway, so it just happens to be how we get our forecasts of day-to-day weather. When you hear that it's going to be cold at the end of the week, this is how we know. It's actually somewhat interesting as to what do meteorologists actually do. Well, a lot of what we do is interpreting these models. We have a lot of models to work with. What's the right one to be using? How do we know? So on. These kinds of numerical models of the atmosphere are how, for example, scientists tend to study weather features. We tend to simulate them using these kinds of models to, in this case, this is, I believe, a model of a hurricane as it approaches the shore of the United States, but it is a type of simulation. Again, this is just a visualization of what's going on in the model. Inside the model, there's all kinds of calculations going on based on the physics of the atmosphere to determine the pressure, temperature, humidity, density, and winds over a region. Okay? And then, of course, to see them moving forward, we are simulating them, we are modeling what the atmosphere is doing. Numerical weather prediction is how we work with climate models. When we are trying to say by the year 2100 the global mean temperature will be this much and so on, what they actually are doing is using models of the atmosphere, usually coupled with models of the ocean and so on, and they are seeing how the planet's temperature is changing on average over the course of like the next 80 years or the next 180 years or however far out they choose to simulate, using these numerical weather prediction or NWP models. Numerical weather prediction models are a type of mathematical model. You might remember that that was in contrast to a physical model. Okay, so the physical models were where you actually built a toy that modeled or reproduced the behavior of a real system. A mathematical model was, of course, where we were using mathematical concepts and language. We had a variety of different kinds of mathematical models, like statistical models and so on. Specifically, a numerical model is based on the equations that describe the actual physics of the system to simulate its behavior. You know, when we were doing the log wind profile, we had a nifty little equation. The left-hand side was u as a function of z, and then on the right-hand side was some terms that kind of describe that shape of the curve of the wind profile. That was our model. It was a mathematical model of what the winds were looking like, but it was basically just a way of drawing a curve that curved the right way and so on. A numerical model is actually the physics. It's the set of equations that actually describes, what is happening to objects based on Newton's laws and the laws of thermodynamics and so on to actually simulate their behavior. And there's a lot of examples of this in science. numerical modeling of a process is in many ways kind of the gold standard of how to come to understand and be able to predict what systems are doing. I happen to just wipe this slide off of some PowerPoint deck you can find online from NASA that actually shows like numerical models of a rocket's flight, where they were simulating how the rocket will fly, and it shows at different heights along the way what are the equations that are describing the forces at work on the rocket and so on to simulate its path. We aren't just saying, oh, the path will be a parabola and then drawing a parabola. That would be a type of mathematical model too. But a numerical model is explicitly using gravity and drag coefficients and things like Coriolis parameter and so on to explicitly compute at every step along the way what are the forces at work on this object. Based on Newton's second law, what does that mean for the changes in the motion of the object and so on. A more down-to-earth, no pun intended, example would be like a video game about cars, like a car racing video game. Now, real interesting car racing games are numerical models. The video game is simulating the behavior of real cars based on their real physics. If the car could drive at half of light speed, turn on a dime, stop instantly, and fire nuclear missiles, it wouldn't be much of a fun game. Right? You'd always see the same outcome of the game, of winning the game. It's because the game follows real physics about how fast can the car accelerate, and the car has to actually stop and get gas. I mean, it's not even a real car. Why does it need gas? Because it's following the rules, and the car goes faster when the gas tank is low because the car doesn't weigh as much, and all this kind of stuff. All the basic laws of the physics of the situation, in terms of like how often you have to change the tires and all that, are being modeled here. This is an example of a numerical model that you've probably messed with. So, the way a numerical model works in general is that if you know the real equations that describe how the physics of a system work, you can usually write some kind of computer program or algorithm that can simulate that behavior to figure out what the system is going to do moving forward. So, the numerical model itself, just to connect the dots here, the model, like the numerical model of the atmosphere, or of that rocket, or of that racing car, is the computer program itself that can simulate the behavior, the real behavior, of that system that you're thinking about. That's what's the numerical model. Numerical weather prediction, then, is based on our actual knowledge of the physics of the atmosphere. The laws of thermodynamics, the laws of motion, things like that. We'll see the exact laws in just a second here. To produce forecasts, whether that's forecasts for what will that big storm system do this weekend, or whether that is how windy will it be near my wind farm, so I know how much electricity we're going to be producing, to how cold is it going to be next week, so we know what the demand on the electrical grid is going to be for heating purposes. That's all numerical weather prediction. It's very integral to the wind power industry. Several of the people I went to grad school with, or have taught since coming to Creighton, have gotten jobs in the wind power in the power industry in general, working with numerical models so that power companies can anticipate either the load on the electrical grid or the yield that they'll get from, say, a wind farm. So to understand the process of numerical weather prediction, your book divides the process up into 4 main steps: observation, assimilation, prognosis, and post-processing. Any textbook would have done it slightly differently. This is a fine way to break the process up. So the first thing you're going to need is observations. All models, certainly all mathematical models, required input. Remember, we had a slide that actually showed that. You can see it reproduced here. So whether that was your log wind profile that needed information about like the roughness of the surface and so on, or whether we're talking about a full-blown numerical weather prediction model that's going to be simulating the weather all over the world for the next few days, numerical weather prediction models are going to have a big laundry list of necessary input in order to run. But they're going to be describing the conditions at the beginning of the model run. Now, broadly speaking, there's 2 kinds of pieces of information that the model is a numerical weather prediction model anyway, is going to be using as input. This is something that we get into more details about like in the electrical load and yield course, or if you take like my science of climate change course. But broadly speaking, there's two kinds of input to a numerical weather prediction model: the so-called initial conditions and the so-called boundary conditions. Initial conditions are the observations that you're gathering from any available platform, whether that is weather stations or upper air stations or whatever, and you are getting information about what the atmosphere is doing right now. What is its temperature, pressure, humidity, what are the winds? We're going to have divided the domain, the area that the model is forecasting, which these days is usually global, although it wouldn't have to be. You might just be making forecasts over the United States or something like that. And you're going to divide that domain up into little boxes, sometimes called grid boxes, sometimes called grid points. And what you're going to be doing is assigning some kind of temperature, pressure, density, humidity, winds, etc. at each of those little boxes. At every box on the map, and we'll divide the atmosphere up vertically into boxes too. So you have this sort of 3D set of these little grids. You'll see some pictures of this in a little bit. And you're going to be trying to assign, based on your observations of temperature, pressure, winds, etc., what you're going to be using for the starting conditions, the initial conditions of your model. Now, these are the observations that are taken by national meteorological services like the National Weather Service all around the world. They're going to be the continuously taken observations of things like temperature, pressure, rains, cloud cover, winds, etc. from surface weather stations and radiosonde weather stations and aircraft pilot reports and ships at sea that send in these reports. Radar stations have ways of getting their observations into the models. Any instrument on a satellite, any instrument on a buoy, any available type of instrumentation that can produce weather observations for the time that you're planning to use as the start of your model run can become part of your initial conditions. Initial conditions are such a key part of numerical weather prediction that it's hard to imagine there's any other kind of input, but there's a whole second set of inputs called the boundary conditions. And the boundary conditions are things that you're imposing. Let's say, imposing being a key vocabulary word there, you're imposing from the outside of the laws of, they are things like the configuration of the terrain. Okay, in your model, the slope of the Rocky Mountains is not going to change. But that's a piece of information the model needs. Okay, or the albedo of the surface of the ocean, or maybe sea ice extent, or the roughness of the Earth, or the albedo of the Earth, or how much radiation is coming from the sun, or concentration of greenhouse gases, or whatever. These are not weather. Okay, we aren't going to be forecasting how greenhouse gases in the atmosphere are changing between now and when that storm system comes through next week. That's not the purpose of a numerical weather prediction, but that's still a type of input, and it's a type of input called the boundary conditions. By and large, these things are not things that are timely. We don't mean like we're going to go outside right now and take a measurement of the amount of greenhouse gases in the atmosphere, or we're going to take a measurement of how rough, what is the aerodynamic roughness length of the surface. Rather, these are typically information that we can get from like a database or a reference work or something like that. We have, built databases of what the shape of the terrain is over these mountains, and then we use that information as input as a boundary condition. Now, there's a whole world of business in terms of running numerical weather prediction models about the relative roles of input conditions and boundary conditions, and like in my Science of Climate Change course, we talk about that quite a bit. Again, feel free to take that class to learn a great deal more about these kinds of models. Now, we're going to be taking all of this input information, whether it is an initial condition that's describing the weather right this second, or boundary condition that kind of describes the configuration and the background physics that we're imposing on the model simulation. But what kinds of inputs we're talking about, we have an issue here. These data are going to be coming from lots of different sources. Surface stations, upper air stations, radar stations, satellites, buoys, ships, pilot reports, etc. They're going to have different errors, they're going to have different resolutions, they're going to have they're not really internally consistent. And so we are going to have to find some way I mean, if a pilot flew over my house today and happened to be turning in a pilot report at that time, and I launched a weather balloon, the truth of the matter is they would not say the same exact temperature. How do we get a consistent idea of what the temperatures and the winds and so on are doing? Well, this is all about that second step that is labeled assimilation. And assimilation is about kind of refining the input that's going to go into the model itself. Assimilation, I wrote here a definition from a different textbook, I think, is the process of taking all the available sources of data and combining it into a single consistent depiction of what the atmosphere is doing. Where we are taking all these different sources of information and combining it to make one complete picture of what the atmosphere is doing over your domain. Again, the domain being the area over which you're making forecasts, and like I said, in modern meteorology that's typically global, although it wouldn't have to be. You can run regional models and so on. Now, so like here's a global model. I just stole this plot from someplace online. You can see how globally we had divided the surface of the Earth up into these little boxes. They're pretty big. In a real model, they'd be much, much smaller than this, but we wanted something that we could actually see with our eyes here. So these guys are, a couple hundred kilometers on each side. That would not be realistic. The resolution of the model would not be adequate. And you can see they also have some vertical height to them. Again, in the real world, in a real numerical weather prediction model, those layers, those boxes might only be a matter of a few tens of meters thick. It's not giant like this. But you get the idea. We have divided the atmosphere up into all these boxes. The domain of the model, which in this case is global, is being divided up into all these little three-dimensional boxes, sometimes called grid boxes, sometimes called grid points. And so we're going to have this global grid, and we're going to populate this grid with the data that we got from our observations. And the assimilation process is what's going to do this. This is a set of software that takes all the available temperature, pressure, wind, cloud cover type information and comes up with a coherent idea of what is the temperature in that box. What is the pressure in that box? Each one of those boxes is just a single value of temperature, or a single value of, and there's a single value of pressure, and there's a single value of the wind speed and wind direction and so on in each of those boxes. A single value will represent what the temperature is throughout that box. That's part of the reason why you can tell they can't be that big. I mean, obviously, a box as big as these, where they're a couple hundred kilometers on each side, would not really have the same temperature throughout. So we can take the available observations and start saying, oh, well, we're going to make this temperature here, we're going to put this one here, we're going to take the average of these two and put them here. There's a whole set of software, there's a whole business called objective analysis that is how this is actually all done. Plus, there's going to be plenty of these boxes had no observations at all. I mean, like ones over the ocean or something like that. There might not be any reports of any data. So sometimes, for example, the assimilation process has to actually use the output of other model runs as input for this model run. And this is a very fascinating process of developing a coherent idea where literally every single box you see on here, we now have a consistent idea of what is the temperature, pressure, winds, humidity, cloud cover, etc. Once the software has come up with all of this, and it's a big job to do it, the resulting complete depiction that is consistent of the atmosphere and what it's doing at your initial time, it has a word. There's a word for that. It's called the analysis. And the analysis will be our final input into the numerical model. It is going to be, these nice three-dimensional grids of temperature, three-dimensional grids of pressure, three-dimensional grids of humidity, of winds, etc., which the numerical model will then integrate move forward, and create forecasts of how that temperature will change, or how that pressure will change, or how those winds will change, etc. But just backing back here for a second, that actual product that you just created, called the analysis, is itself a really cool thing. I mean, like, here's an example of and again, it just happens to be the North American model, or NAM, analysis for a particular day in 2016. And you can see that the model, based on all the available observations, came up with maps. This happens to be 300 millibar wind speeds, which are colored. The contour lines there are 300 millibar height, how high above the ground you had to go to get the 300 millibars. And then the little vectors on there are showing us the winds. And you can see how on a grid at 300 millibars above the ground, we now have at every one of those little spots an idea, an internally consistent idea of what is the wind speed, and in this case height, and whatever the other one was, the wind vector. We could, that's useful, that's a handy thing to have. In fact, here's another one. This happens to be closer to the ground. This is 850 millibars over Europe. And again, you can see like the height and the winds and the temperature are on this particular plot. So the colors there are showing you the temperature. And again, if you actually look at like where the spots are for each of those vectors there, you can see how it's a grid. It's a three-dimensional grid, and at every one of those spots, we know what the temperature is, the wind speed, the pressure, etc. This is a huge amount of work. Plenty of people make their careers in how models assimilate data into these analyses that become their input. And frankly, they're pretty darn useful themselves. These analyses are a useful research tool because they are a state-of-the-art tool for describing the current state of the atmosphere at any given moment. Somebody put an enormous amount of work into depicting what is the atmosphere doing all over the world right now. That's really cool. And so all of these analyses that are created as input for the numerical models are actually all saved and used as a standard tool when we're researching weather and climate. These numerical models are going to be run at national entities like the National Weather Service or the European Center for Medium Range Weather Forecasts and the Japanese Meteorological Agency and the UK Met Office and so on. All of these entities have these models and they run them about every 6 hours based on the latest observations that come in from all around the world. But the analyses themselves are pretty damn useful. And we save them, and in fact you could access them from lovely websites like the one I have shown right here, where, like, for example, this happens to be a particular, let's see, which one is this? This is using a model called NZEP-NCAR that is creating a set of analyses, and you can go to this website and tell it you want a map of temperature at this analysis level, maybe 1,000 millibars, you tell it what day you want, and it'll actually go back into a giant database and pull up maps like this one that happens to be a particular day's surface temperature. This happens to be January 5th, 2010, the day my oldest child was born. And if you notice, it looks a little cold around Omaha. And in fact, the model analysis at that time was 255 K, which I think is 3 degrees below 0 Fahrenheit. On the way to the hospital when my wife was delivering the baby, it was 17 degrees below 0, according to the thermometer on the car. Anyway, so I just pulled that one up just as a way to illustrate just any arbitrary day at any arbitrary time, you can find these analyses. I mean, all the available observations from satellites and surface stations and whatever else is buoys at sea and all that kind of stuff have all been assimilated into this nice consistent picture, which at that time, on 5 January 2010, was being used as input into the numerical weather prediction models to make forecasts of how the weather was going to change. But we can just use them for weather research now, and case studies and so on. Now, before we go forward and talk about more of the steps in the process of numerical weather prediction, let's actually answer a couple quick questions. Question 1. What is the input to a numerical weather prediction model? Is it A, the basic laws of physics of the atmosphere? B, the weather conditions at the start of the model simulation? C, random numbers? Or D, our forecast of the weather conditions at some point in the future? One of those doesn't look like a very good answer, but in general, go ahead and make a choice for those 4 options and get a little feedback before you move on to question 2.